Hello students, welcome to Chapter 6b, Part 2. We're going to be looking at p-values now. P-values are basically just another way, an alternate way to determine whether to reject a null hypothesis or not reject a null hypothesis. The decision rule is quite simple. Reject the null hypothesis if the p-value is less than alpha. Remember, the alpha value is given to you. That's the level of significance, the risk of making a type 1 mistake. That's given to you in the question. P-value is something we will have to calculate. The calculation process is actually very similar to what we did back in Chapter 5, I believe. So, what is a p-value? Basically, p-value, right in here, remember we are observing something in the sample, and we are comparing that to something assumed to be in the population. So we assume something in the population is true, that the average height or average weight or the average money spent or the average income, we assume a value exists in the population. For whatever reason, we don't believe that value, so we take a sample and we compare the sample data to that assumed population value. So a p-value is the probability of observing the difference between a sample and the population value. If p-value is really, really small, it basically means the probability of getting sample data, or the probability, p-value is a probability of getting the sample data measured against the population value, so the assumed population value. We'll work on an example of this. But this statement here, very small p-values indicate the strength of the decision, and that there is little probability that the null hypothesis is true. So really, really small p-values basically indicate the strength of your decision to reject the null hypothesis, because there's very little chance that the null hypothesis is true. Remember, the population value is going to be the null hypothesis. We take a sample to test it. If the difference is really big, basically means that something's wrong, and what is wrong is the assumed population value. So we're going to find a p-value from the z-test statistic. Remember, the z-test statistic is the z-value that we actually calculate. We compare the z-test statistic to the critical value, z-alpha, but this is the z-value that has a formula. So we calculate z, we find the area for z, and we always subtract it from 0.5. If it's a two-tailed test, and there's keywords that will tell you if it's a two-tailed test in the question, we double that value. So this process here, this is like similar to the three-step process that we used back in Chapter 5 when we were calculating z, or calculating a probability of something. So calculate z, find the area using the normal distribution table, and then subtract it from 0.5. So let's work on a little example. This example is from the handout I gave you based on hypothesis testing, Chapter 6b. So a consumer purchased one of those new and improved light bulbs, advertised to last at least 1,000 hours. So right in here, this is a key word. The consumer believes that the light bulb doesn't live up to the manufacturer's claim. So this starts the whole hypothesis test. We, as the consumer, don't believe that the company actually is correct when they say that their batteries last at least 1,000 hours. So he tested 40 light bulbs. Basically, you'd go out and buy 40 light bulbs, plug them in, turn them on, and see when they actually die. he found that the average life was 960. So yes, 960 is less than 1,000. However, when we sample anything, sampling, we take a small number of items. Sampling is not 100% accurate, but it saves time and money. We could have tested every single light bulb this company produced, but that would be really expensive. And we would need a lot more equipment and things to plug in for these light bulbs. So we just bought 40 of them. So just because 960 is less than 1,000 doesn't mean that the consumer is correct, saying that it doesn't last 1,000 hours, because is 960 close enough statistically to 1,000? So the population standard deviation is known to be 100 hours. First part, is this a one-tailed or two-tailed test? This is definitely a one-tailed test because words like this. Remember, a one-tailed test is going to have words like more, less, greater, at least. Whereas a two-tailed test will have a word like different than, or that the light bulb is advertised to last 1,000 hours. So it is 1,000 hours. And then we test to see if it's not 1,000 hours. So that's a two-tailed test. Words like equal or is or different. Those are going to be the key words. So at the 1% level of significance, so alpha is 0.01, are the light bulbs significantly less than the manufacturer's claim? And then gets us to calculate the p-value. So let's look at what the null hypotheses would be. Let's use red. The null hypothesis, the manufacturer's claim, beginning statement, is that the average is at least 1,000 hours. At least is greater than or less than. We're going to test to see if it is significantly less than 1,000 hours. I'm going to write down the data we have. We have sample size is 40. Sample mean we got, the average we got from our sample is 960 hours. Population standard deviation is 100. And I'm just going to write the level of alpha here as well, 0.01. So it's a one-tailed test. Let's calculate the test statistic first. We use this formula here. So this is going to be 960 minus 1,000 divided by 100 over the square root of 40. And this works out to be negative 2.53. Next thing we'll need to do is find this value, or remember what this value is, Z alpha. This is the critical value, that threshold value, the value we're going to compare our test statistic to. Z alpha, if alpha is 1%, our test statistic is 2.33. Remember, in the beginning of this chapter, we went through various levels of alpha, and if it was one-tailed or two-tailed, what the critical value would be. So this one, critical value is actually negative. Our test statistic is negative. Critical value is going to have the same sign. Let's switch pens here. I'm going to write down our decision rule. Reject the null hypotheses if the test statistic is greater than a critical value. With a little statement here, use absolute values when we are making the decision. Now, even though the values for Z are both negative, we are going to just pretend they're positive for the decision. So we will end up rejecting the null hypotheses because 2.53 is greater than 2.33. 2.33 is our critical value, or that threshold value. Our test statistic, our value we got from our sample, is greater than our critical value. So we will reject the null hypotheses. Rejecting the null hypotheses basically tells us that this statement here is wrong. And we're left with this statement here. Oops, got to write an A in there. The null hypotheses. Which basically means that we have enough evidence to tell a company that, hey, your claim is not true. Your batteries are not lasting at least 1,000 hours. We don't know how long they're lasting, but they're definitely not lasting 1,000 hours. So the last part of this is calculating a p-value. Go to a new sheet here and calculate the p-value. And just as a reminder, we have already the test statistic, 2.53. So this is how we're going to find the p-values. We calculate the test statistic, which we've already done, 2.53. We're going to go to our normal distribution table right here and find 2.53. So the area that corresponds to a Z value of 2.53 is 0.4943. So this would be like step 1, step 2, area 0.4943. Step 3, the answer is the p-value equals 0.5, always 0.5, minus, and it's always minus, 4943, which equals that value. If this were a two-tailed test, we would double this value. But we know that it's a one-tailed test because of the key words in there. It said at least. Now we can also make the same decision using the p-value approach. Reject the null hypotheses if the p-value is less than alpha. We are going to reject, we are going to reject the null hypotheses because 0.0057 is less than 0.01. That was a level of alpha, level of significance. So that's why we are going to reject it. Because the p-value really small. Basically, the p-value tells us that there is, that would be 0.57% probability of observing a difference between the sample data, which is correct, versus the population claim. The population claim is just a number that someone believes in. So there's a 0.57% chance of witnessing something with this type of a difference between the sample and the population. So something must be wrong because it's a really, really small probability. And what is wrong is the population, or not the population, but the hypotheses that the company claims to be true. So they are wrong, and that's why we are rejecting the null hypotheses. So we reject it because of the p-value, and your decision will always be the same, and we are rejecting it here, based on the standard or the classic hypotheses approach where we compare two Z values. So both decisions will always give us the same final result. So that's our discussion of p-values.